But still, the selection sort probably isn't the way you would sort a list. You'd likely use something like a hybrid of the two methods. You'd check the second value, and if it was lower than the first, you'd move it to the front. Then you'd check the third value, and you'd place it in order with the first two. If it was the lowest of the first two, you'd move it at the beginning. If it was the highest, you'd leave it where it was. And if it was in between them, you'd move it in between. So that's the way an insertion sort works. It effectively moves one item at a time through the list and puts each item in the right location relative to the items that have already been sorted. So the first time, it compares the first two values and puts them in the right order relative to one another. Here, 3 and 7 are already in the right order, so nothing changes. So when we hit row 1, the algorithm is guaranteed that the first two items will be correctly sorted. Now that it knows the first two items are correctly sorted, it's going to look at the third item and put it in the right location relative to those first two. If it was lower, it'd put it first. If it's higher, it would leave it where it is. And if it's in the middle, it'll move it in the middle. And sure enough, 6 is between 3 and 7, so it moves it to the middle. So at the start of row 2, it guarantees that the first three items are in the right order, so it looks at the fourth. 1 is less than any of those numbers, so it moves it to the beginning. So now it guarantees that the first 4 items are in the right place, so it looks at the fifth item, and it's already in the right place, so it makes no change. Now it knows that the first 5 items are in the right place, so it looks at the sixth item, and it finds that it belongs between 7 and 9, so it moves it there. It continues that until on the second to last run, it guarantees that every number except for the last number are in the right place. It then looks at the last number, finds where it belongs, and moves it there. Once it's processed that last number, it guarantees that the list is in the correct order. Notice the high-level pattern here. Before we were noticing that at every given run of the loop, an entire column would become correct. Here we see the opposite. The last column is wrong until the very last run of the loop. The second to last column is wrong until the second to last run. The third to last is wrong until the third to last, and so on. So the pattern looks kind of similar, but in reverse. We have long columns with the wrong numbers in place, starting at the top, as opposed to long columns starting at the bottom, with the right number in the right place. Like selection sort and bubble sort, insertion sort still runs in O of n squared. It runs once for each item in the list, and within each run, it compares it to every previous item in the list. So it puts each item in the list in order, but to do so, it will compare each item to every previous item in the list, which can get to be a lot of comparisons if we get a really long list. In practice, bubble sort is less efficient on average than selection sort, which is less efficient than insertion sort. However, all three have the same worst case scenario, O of n squared. Now, can we do better? We definitely can.